Okay, so I'm going to be talking about the solar dynamo flux budgets. Everyone can hear me?
Yes, we can hear you.
Okay, good. Okay, and so this basically comes from applying Stokes Theorem to the induction equation. I'm not dropping any terms, I'm just applying Stokes Theorem to the induction equation. And what we find is the flux for any area is a conserved quantity. If you want to change that amount of flux on that surface, you have to bring it in across the boundaries. The reason why this is, of course, true for anything for the induction equation all the time, but it's interesting for the solar dynamo, the global solar dynamo, is a particular simplicity of the field. So the radial field has a nice simple structure at minimum. The field is concentrated at the poles, and the toroidal field has a simple structure that's all the maximum when all the toroidal field in one hemisphere is of the same polarity. And we have 4 cycles, and this particular data is taken from WSO. So the toroidal flux budget, we get very simply, we choose as our surface the northern hemisphere and equatorial meridional plane, and then the change in the flux through that surface, the phi, so that's the b phi through that surface, becomes a surface integral. The large scale component of which is 0 except for at the surface, and the surface components, both the large scale and the small scale, are completely observable. If we observe them, we find the large scale part corresponds to the omega effect. It's given by the differential rotation at the surface times radial magnetic field at the surface times some geometrical factors. And you can estimate this, and you find 5 to 8 times 10 to 23 Maxwell's per cycle per hemisphere. You can also determine the small scale contribution, the contribution from the small scale components at the surface. It's called by the observers flux emergence. It's 2 bits. One of them is vertical flows carrying horizontal magnetic field across the surface, and this is flux emergence. The other bit is also 0 away from times the flux emergence, and this we can tell because we have observations at high resolution going for several cycles. And this, anyway, this term corresponds to a loss of about 3 times 10 to 23 Maxwell's per cycle per hemisphere. So more than half of what you generate by the omega effect, you lose through the surface. And so now we can make a nice little image of this. On the bottom, we have the winding up of the field. So BR times the differential rotation times the geometrical factor. The sign lambda is in there because I want to average both hemispheres together, and they have different polarities in each hemisphere. This goes on to the x-axis in the plot on the right-hand side. On the top row, we just have the loss due to the toroidal flux. So the toroidal flux times the velocity at which we see it coming through the surface. So all of these are observable. We've observed the surface toroidal field. We observed the velocity at which it's carried through the surface. We observed the radial magnetic field. We observed the differential rotation. And what you find is that we have a nice little loop. We have 2 magnetic cycles here, 4 activity cycles, 2 magnetic cycles, and the magnetic field just goes around and around in little circles with some noise. The noise, to consider the noise, we have to look at what's happening to the poloidal field, the R component of the field. And at solar minimum, when the polar fields are strongest, all that field is concentrated at high latitudes. So here we have the contribution to the total flux as a function of latitude, and you can see it's more or less 0, except above about 50 degrees, where we suddenly are storing all the field at the end of the cycle. And the distributions are not very different from cycle to cycle. So here we have cycles 20, 21, 22, 23. 23 is the one which is slightly higher because it was observed with a different instrument, but they're all very similar. The Poloidal flux budget you get from just considering the change in the radial field through the photosphere in the northern hemisphere. Again, we begin with Stoke's theorem. In this case, the large scale flow at the equator, at the photosphere, vanishes, both the UR and the U theta components of the flow. And so we only have small scale elements. These small scale elements are again observable. These are things which it's no difficulty for observers to see at least half the time, and the other half of the time you assume is statistically similar. The first term is URB theta. This is flux emergence across the equator. Flux emergence of highly tilted field across the equator. And here we have two examples. In the left panel, you can see the red circle. These are different Carrington rotations. We begin with almost nothing in the red circle. Carrington rotation later, we have something emerging. It's actually something quite big, which takes 3 or 4 Carrington rotations to fully emerge. And the point here is this is very effective at carrying flux across the equator. The example on the right-hand side is a similar event. The important point is that, not surprisingly, the observations, the induction equation, and Stoke's theorem all work together to tell the same story. And the story is, if all you're interested in is the net flux in the hemisphere, which is going to become your axial dipole moment, it's going to become your polar fields, because at the end of the cycle, all the flux is swept to the poles, and all you need to do is look at the equator. And if you do this, in this case, we have the observations from MDI, so cycle 23 to 24 was a mystery why cycle 24 was so weak. And this was equated with the weak polar fields at the end of solar cycle 23. And it turns out, if you want to get the weak solar fields at the end of solar 23, you have to include the actual observed tilt angles. And this was of the emerging regions, because this is where the noise is coming from. And this is why cycles vary from one cycle to another. It's because these tilt angles have a huge scatter in them. Joy's law is a statistical law only. And so this was worked by Jia Jiang in 2015 and also Whitbread in 2018. Of course, so the budgets paint a very nice picture of the fluxes present in both hemispheres, but you need to move those fluxes around if you actually want to reproduce what we see on the sun. In particular, the differential rotation acting on the radial field creates toroidal field at about 55 degrees. This was explained by Sprout in 2012. It's just because this is where the differential rotation has a nice strong gradient. And we see the emergences at 35 to 5 degrees latitude, so close to the equator. So we must be moving the field somehow, either through small scale correlations between the magnetic field and the velocity field, or via large scale flows carrying the large scale magnetic field. And here Gizon et al. In 2020 showed that the large scale flow acting on the large scale field was sufficient to explain the migration. On the other hand, at the surface, the flux emerges at low latitudes. It has to cross the equator, which is why the emergence at low latitude is so important for the dynamo. But it needs to be carried somehow to the poles so that it can be acted on by the differential rotation for the next cycle. And here again, it has to be a small scale correlations in the small scale quantities, or the large scale meridional circulation at the surface carrying the field to the radial field to the surface. And the observation shows that it's mainly the large scale field carrying the large scale radial field to the surface, to the poles. The critical bit, which I haven't discussed in nearly enough detail, is the role of flux emergence. So flux emergence is the source term for the Poloidal flux. It's basically this tilted flux emergence near the equator. And the leading or the prograde polarity gets carried a little bit more across the equator. So this is the systematic component to that part of the flux budget. or the emergence across the equator by highly tilted active regions are the source for the poloidal field. The flux emergence also has the important role that it's the loss term for the toroidal field. So we saw the field is generated by the differential rotation winding up, but it's lost due to flux emergence.
Robert, a couple minutes left.
Yeah, so this raises the question of what is flux emergence? Is it mainly a passive process where the external velocity field plays a huge role? Or is it something where the flows in the flux tube play a huge role? Or is it some mixture? This is hard. What I want to say is the observers do a fantastic job of measuring flux emergence on all scales. So here we have 7 orders of magnitude where they've measured this flux emergence occurring. And this, I think, is where HMI is going to, or is proving its value, is in understanding the flux emergence processes much better. So this is a result from Hannah Schunke, where she finds that they emerge east-west, and afterwards they move more or less in straight lines towards some locations. And this was looking at a number of active regions. So my conclusions are we have, from very simple Stokes theorem applied to the induction equation, poloidal flux balance, toroidal flux balance, and we also have a key role for HMI in understanding flux emergence. I will stop there.